Hi everyone, this is Mr. Moreau, and I'd like to go through just a few details and clarifications with our Human Evolution Skull Measurements worksheet. So right off the bat here, you can see that I've just very simply highlighted and color-coded some key physical features of both the chimpanzee and the human listed here. And what this picture should allow us to do is really just kind of navigate and understand some details and some differences between the modern human you see on the right and the chimpanzee skull you see on the left. Now remember, the misconception that students often have prior to learning anything about evolution is something like humans evolved from monkeys, humans evolved from apes. It's more correct to say that humans evolved from a common ancestor, which we share with monkeys, which we share with apes, but that doesn't mean that the chimpanzee is more primitive, or that we evolved from something that was just like the chimpanzee. It's more correct to say that we evolved from a common primate ancestor, and the details of that chimpanzee skull are most likely more similar to that ancient primate common ancestor. So the comparison between the modern chimpanzee and the modern human does help us understand the differences between our modern physical features and more ancestral primate physical features. So as you read through those color-coded physical details there, that should help us understand some differences from where, physically speaking, where our ancestors were in terms of their skull features and where we are today and the differences between. Now what I really want to focus on here is this section, and that being an easier way to kind of visualize how to take measurements of skulls and what these indices mean. So you can see that at the top of the screen here, I've just color-coded and highlighted those measurements that we take on the skull, and down below there I've used the same color to highlight the description of that measurement in the table. So I want to just go through and talk about the significance of each one of these and make sure that you understand what we learned because of these calculations. So first, the cranial index. You can see that you'd have to measure across the front of the skull, specifically the cranial region. That's the place in the skull where you'd find the brain. So take that green measurement and divide it by that orange measurement. And it's no surprise to you that because these are both related to the cranium, which is where the brain is found, a larger cranium is indicative of a more modern species because, as our book pages taught us, a large brain is a very distinctive feature that is part of the Homo genus, which is a very recent evolutionary event or group of the hominid species, the various hominid species. Now the next one, skull proportion index. You can see that we're going to take the green cranial breadth measurement and divide it by the blue facial breadth measurement. And for this one, it's helpful to know that blue facial breadth measurement, if you actually put your hands, your fingers right on your cheekbones and then sort of slide your fingers back towards your ears, you can see that cheekbone kind of is part of this whole arch. And that arch of bone actually resides above a lot of muscles that control our jaw. So a wider facial breadth actually means that there's more room for larger jaw muscles. And as we have evolved throughout human history, our jaw and therefore our jaw muscles have become smaller over time. So a smaller facial breadth with respect to a larger cranial breadth would be indicative of a more modern species. Therefore, the cranial breadth to facial breadth ratio, which is what we're calling the skull proportion index, the larger that is, the more modern the species must be. Right? Because the cranial breadth is the numerator of this calculation, the facial breadth is the denominator. If the facial breadth is bigger and the cranial breadth is bigger and the facial breadth is smaller, that means that fraction of cranial breadth divided by facial breadth will be a larger number. So the larger the number, the larger the skull proportion index, the more modern that fossil most likely is. Next up is the facial projection index. And I kind of think of this as like the caveman index. If you think of if you kind of picture what a caveman would look like, an ancestral human species, they kind of have this like front pushing snout-like face with like a big jaw and their mouth, their lips kind of like protrude outward, rather than having a more modern flat face like we do today. So for that reason, the facial projection index is going to be another good indicator of how modern versus how ancestral the species is. For the facial projection length, you take the yellow facial projection length and divide it by the total skull length. So the yellow line divided by the pink line. Therefore, the larger this index is, the more ancient the organism would be, right? The longer that yellow line is, the bigger the jaw is in proportion to the rest of the skull. And that is not a characteristic that we have as modern humans, right? Our jaw is much smaller compared to our larger cranial length. So for that, or the total skull length. So for that reason, the smaller this index is, the more modern the fossil is. The larger it is, the more ancient it is. So that's true for facial projection index. The next one, skull and vertebral attachment index. Now this one, which our book pages talked about extensively, is all about where the spine enters the skull. Now that purple line is going to tell us how far from the back of the skull does the spine enter. Now the longer that purple line is, the more toward the bottom of the skull the spine attaches. Okay, so imagine that purple line being much shorter. That would mean that the skull attaches more toward the rear of the skull, and that is going to teach us a lot about how the organism moves. If that hole at the bottom of the skull through which the spine goes, if that is more under the skull, that is probably an upright, two-leg walking, bipedal organism. So the further back that hole is at the bottom of the skull, the more likely that this organism is ancient in that it is not bipedal. Two-leg walking, bipedalism, that is a more modern or recent development in human history. So you can see that we take the purple line and we divide it by the pink line. So the larger this index is, the more modern that organism must be. And finally, canine incisor index. From our Your Inner Reptile video, there was a lot of talk about teeth, and long canines were a major feature of early mammals and are common features in many of our other primate cousins. Therefore, our primate common ancestor that we share with all other primates also had long canines. Therefore, for this ratio, when you take the red, or the length of the incisor, and you divide it by the length of the canine is just a fancy word for like your fang, like your vampire type teeth. So the longer the canine is, the more ancient you expect that organism to be. Therefore, if the brown line is larger, so the denominator of that fraction is larger, that would make this index smaller. Okay, so the smaller this index, the more ancient the species. The larger the index, the more modern the species. So that was an important kind of clarification for a lot of these, teaching us why these measurements matter and what we can deduce from them when we compare one to the other.